Hello, students of statics. This is Dr. Dan Baker with a video today looking at an example of how we can take a moment 4 different ways. In the previous video, we talked about there was 4 ways to take a moment. Let's see that in action on a 2-dimensional moment. So the scenario we'll use for all 4 of these solutions is the following. So here's my axis system. We're going to go with a horizontal X, a vertical Y. And we have a location right over here. It's going to be 4 units to the right of the y-axis. Call this point A. And another point that's up here, let me label these distances. So this is 4 inches. The distance unit we'll use is inches. So 4 units from the origin and then 6 inches vertically off the x-axis, and we have another point. This point we'll call point B. And we're going to connect A and B with a position vector. We're going to call this position vector R of AB, and then we're going to pass a force vector through point B. Here is our force vector, a little shallower angle than the line of AB. This is a 200-pound force, and this 200-pound force is defined by an angle which is proportional to a 3, 4, 5 right triangle. So this would be the 3 side, this would be the 4 side, and the 5 side there along the hypotenuse. Okay, so you could either solve for that angle if you wanted to, or you can go ahead and just leave it as a 3, 4, 5. I'm going to leave it as a 3, 4, 5 because it makes actually our math even a little bit easier to compute. So you may remember that there are, like I said, 4 different ways we can compute this. We're going to start with a vector determinant. Okay, so number 1, I'm going to go in the same order that we did in the notes in the previous video. So a vector determinant. You can't go wrong with a vector determinant. It will compute any 2-dimensional or 3-dimensional cross product. It can be a bit laborious, as we'll see here, if you have information that's fairly clear in a 2-dimensional problem. But let's set this up. So we're going to take our RAB crossed with RF. So in all these cases, let me just write here, we want to find our moment about point A. Let me talk real quick about what kind of physical scenario we might have. Let's say that you have a small rectangular plate. I'll kind of sketch that on here. So you have a rectangular plate, looks something like that, and that you put a pivot point right through point A, and then you attach a cable, and you're going to pull on that plate through point B at that given angle with a 200-pound force. Okay, so I give you something physical to think about. What would it look like to basically come up with a scenario to say, why would we want to solve for that moment at A? So our moment at A is a vector and is equal to this cross product. So in determinant form, we know that in the top row, we're going to put our unit vectors, I hat, j hat, and k hat. In the next row, I'm going to put my components of my position vector. Okay, so components of position vector, I have 4 inches going in the negative x, so that's going to be a component here of -4. I have 6 inches in the positive y, so that's going to be +6 in the j hat. And because it's a 2-dimensional problem, nothing's going in or out of the page for a distance. The force is going to have similar x and y components and no z component. It will also have a negative x component. Let me write this one out as negative 4/5 of 200. We can use the 4/5 because as we zoom in here, that the 345 is basically proportional to a 200-pound force. Let me add in the components of this 200-pound force. Call this Fx. Call this one coming up here Fy. And so fundamentally, my 345 is proportional to my, I'll call this one Fy prime. It's the same length as Fy. It's just on a different line of action. So I try to call it a different name. But essentially, my 345 is proportional to my Fy to fx to 200. Okay, so two proportional triangles, and we know these two triangles are proportional because they share exactly the same angles. They're both right triangles. They both share this angle right here. I'm going to call this, we'll use this a little bit later, I'm going to call that phi. And I certainly could solve for phi if I wanted to, right? Phi is going to be the inverse tangent of 3/4. And then if you took the sine of that angle, you would end up with 3/5. If you took the cosine of that angle, you'd end up with 4/5, right? Because the cosine is adjacent and the sine is opposite. All right, so enough about that for now. Let's go back over to our determinant. And so my next term here is going to be that y component. It'll be positive 3/5 times 200, and then 0 here in the k hat. Now you could do the diagonals to solve for this. You could realize that all of your I hats and j hats will be 0 because of these two zeros right here and here. But any way that you slice it to solve for this determinant, you're going to end up with a -4 times 3/5 times 200 is 120. And then on the negative diagonal, right, talking about this diagonal right here, this is going to be negative times the terms on that cross, and that will be 4/5 of 200, which is minus 160 times that 6. Okay, so and this entire thing is times k hat. Okay, you're actually multiplying these terms times that unit vector. So let's get that included on this step as well. So there's my k hat. Punching through the math, I end up with 480 inch-pounds in the k hat. Okay, so this is my moment about A, and it is a vector because I included the unit vector. If I didn't include the unit vector, it would be a scalar. Okay, so there is my vector determinant. The next way that I could solve for this moment is using these angles. So let me zoom back in here. I have a couple more angles I need to find. One of those angles is going to be this angle here. Let me call this one alpha, and then I know this one's 90 degrees. Okay, so that one's quite easy. So we can write here that phi, we know, is the inverse tangent of 3/4. I could have used other inverse sine or cosine, but I chose tangent. So therefore we find that phi is equal to an angle of 36.87 degrees. Notice that a 3, 4, 5 right triangle is not a 30, 60, 90 right triangle. I see students make that assumption quite a bit, but we see that it is in fact a 36.87, 90, and whatever 36.87, or 90 minus 36.87 is equal to. And then our alpha is equal to, I can also use an inverse tangent here, so I have an inverse tangent of 4/6. And that is equal to a value of 33.69. So in order to find my overall angle, all the way from here to here, call this angle theta, we could find that theta is equal to 90 degrees plus 36.87 degrees plus 33.69 degrees, which gives me a theta value of 160.56. All right, so given that information, the angle between the two vectors, we can write that, number 2, if I want to find my moment using basically the lengths plus angles, we'll try it that way. We'll say lengths plus angle. And that is in the form that the moment about point A as a vector is equal to the length of our AB times the length or magnitude of my force F times the sine of this angle between them, which is theta, and that's going to be times that unit vector u hat, which is going to come from the right-hand rule. Okay, so that's one of the challenges here using lengths and angles. You do have to do a manual right-hand rule. So we could put 4 and 6 through the Pythagorean theorem, 4 squared plus 6 squared square root. We end up getting a length of 7.21 inches. That times my force of 200 pounds times the sine of our theta angle, 160.56 degrees, times u hat, and this also equals 480 pounds. Now for the sine, remember that the sine on this fundamentally is going to be, well, the direction is going to be either into the screen or out of the screen, right? Any two-dimensional cross product, two-dimensional moment can only have k hat components. It doesn't matter if you cross an I hat component into a j hat or a j hat into an I hat, that you can only get positive or negative j. And so on this problem, if you slide your fingers or point your first finger in a three-finger cross product along RAB, and then curl your fingers into the force vector right here, or if you're using a three-finger cross product, point your second finger in that direction. Now you'll notice that these are not perpendicular, which is one of the reasons that I don't always prefer the three-finger cross product, because in a three-finger cross product, you tend to hold your fingers orthogonal, and if vectors aren't orthogonal, it gets to be a little bit strange. But if we slide our fingers along AB, we have to turn our hand so our thumb is up in order to curl our fingers around to the left. And so your thumb should come out of the screen, and we get a positive k hat from the right-hand rule. Okay, so we can write that here as a positive k hat from the right-hand rule. Okay, so same value for technique 1 as technique 2. Just different pathway to get there. Next, let's look at number 3, and 3 is basically finding a perpendicular distance. Now I'm going to sandwich all these kind of in together just to save some room on the page. So number 3 is we want to find a moment about A is equal to D perpendicular times F. So with F, there's no work to do. We know the magnitude of F is 200. D perpendicular is not the easiest thing to find. Okay, let me zoom back into my drawing since I already have it here. I'm going to move a couple things around. Let me get rid of that highlighting and get rid of that highlighting, and then move this label here, RAB. And I did that because I wanted to leave myself some space to draw out the line of action of this force vector. So here is my line of action, trying to stretch straight out from that 200-pound force. And so really the value we're looking for is we're looking for a position vector, which is going to go right here from A up there to that line of action where this is a right angle. Okay, so this we could call our D perpendicular. All right, so as we look at this system, what we see is basically we need to continue this 3/4 slope. Okay, let me label that on here, that our line of action has a 3/4 slope. It's actually a negative 3/4 because of the direction it's going, just like our force vector had a 3/4 slope. Okay, so if we drop 3 inches for every 4 that we go over, okay, so basically at 3 inches down, we'll be over here at 4 inches across. At another 3 inches down, we'll be another 4 inches across. Okay, I'm just using the definition of a slope to know my rise over run, or change in x over change in y. And so I figured out that as I follow that line of action, my 200-pound force, I can trace that down to an intersection point that is 8 inches to the right of the origin. Okay. Now, it also very importantly tells me that this distance along here is 4 inches. Okay, and I'm going to use that in my computations. Now, the next thing I need to know is what's going on with this angle. Well, one thing that if you had already computed, if you wanted to, the angle of phi, we know that this angle here is also phi. Okay, I know that angle is also phi because fundamentally I have that this line, which is parallel to the x-axis, is bisected by this big line of action. And we know that any two angles that are along basically a line bisecting parallel lines are going to be exactly the same. So you can go ahead and put that if you wanted to as the 36.87. Now I also know that I could use a similar triangle here if I wanted to, and with that similar triangle I could come back in here and I could map a 3, 4, 5. Now noting my 3, 4, 5 is in a different orientation than it was above, but it still has the same angle, phi, that's right here. And so it turns out that this is still going to be a 3, this is going to be a 4, and this is going to be a 5. Okay, so either using the angle phi or this new 3, 4, 5, we essentially can use that then to determine what our D perpendicular is. Okay, so to write out those computations, get my zoom somewhere close to correct, we can write that 3/5, which comes from our 3, 4, 5 right triangle, is similar to or equal to my 4, let's see here, I want the D perpendicular, my D perpendicular divided by 4 inches. Okay, so what this really is this is the side opposite phi divided by the hypotenuse is equal to, again here, the side opposite phi divided by the hypotenuse. Right. Once again, if you wanted to, you could go ahead and do a sine of phi. Sine is going to be the opposite over the hypotenuse. Rearrange that, solve for that opposite, which is D perpendicular. Just showing some of the flexibility in our math. So we can solve here that D perpendicular is equal to a value of 2.4 inches. Now I do need to add here, if I'm solving for the moment vector, we still have to have this u hat, right, added in or multiplied into our scalar. And so of course 2.4 times 200 gives me a moment about point A, also equal to 480 inch pounds. And again, the sign on this is going to come from observation. Okay, so same justification we used for the previous one. Now in this one, you could look at this perpendicular D, right? Instead of focusing on your RAB, you could focus on crossing the yellow one here into that force along its line of action. So these are perpendicular. And so if using the 3-finger right-hand rule, or once again, slide your fingers, start at A, point them along D perpendicular up in this direction here, and then push them, curl them into that force, and your thumb should come out of the screen. And so that gives us a positive K hat. Once again, from the right-hand rule. All right, so there is technique number 3, also with the same answer. 480 inch-pounds in the positive K hat. And the last one we're going to look at is using what's called the method of moments. It also is known as Varignon's theorem, which is kind of a fancy name, but really what we're going to do with the method of moments, or Varignon's theorem, is we're going to focus only on the perpendicular components. Okay, so I'm going to redraw this here quickly just so we can see these perpendicular components, really highlight them versus the full vector. Okay, so coming back here, here's my x, here's my y. Now I'm going to redraw this position vector as my r, I'm just going to call this rx, it's rx of AB, and then coming up this direction here would be my ry. And then my force vector is going to be made up of 2 different components. One of those is going to be my fx, and the other one is going to be Ooh, I made an error here, and let me talk through what that is before I get into that FY. The error I made is that it's a dangerous habit to get into moving your line of action of forces or of position vectors. Okay, notice as I drew my RY right over here that essentially I took a vector whose line of action went through point A, and it no longer goes through point A, and I moved it over a distance here. So fundamentally, you want to leave your even component vectors still going through their origin point. So let me just call this ry prime. Now, of course, the length of ry prime is exactly the same as ry. But let's go ahead, given that notion about not wanting to move vectors off their lines of action, let's leave that there, and let's put this here as fy. Okay, so fundamentally, I've just basically changed my two position vector and my force vector into components. Okay, and as components, we can take a look at them and see that it's only the x component of our position vector that gives us a non-zero moment with the y component of the force vector. Okay, and likewise, it is the y component here of the position vector that gives me a non-zero moment with the x component of the force vector. Okay, those are the perpendicular pairs. So if we have these two perpendicular pairs, what we can do is we actually take the cross product of each one of these. So we can say that my moment about point A is equal to my Rx as a vector crossed into my Fy as also a vector. I'm going to add that to my other pair. So my Ry crossed into my Fx, always R cross F for any moment. And so now when I take a look at these, essentially I just need their distances, and I'm going to determine their sign from the right-hand rule. So my distance Rx is 4. Now notice I didn't put a -4. I'm only going to have an overall sign of this term from the right-hand rule. Now, we already computed the y component. The y component here was 120. Again, I'm not going to worry about a sign there because the sign comes from the right-hand rule. The right-hand rule tells me I need to cross Rx into Fy. Slide your fingers along Rx, put your fingernails toward this arrow tip. You're going to need to rotate your hand. It gets a little bit uncomfortable. If you're doing the slide then cross, in order to curl your fingers up to Fy, curling them up and away from you, your thumb should go into the screen, which is negative from the right-hand rules. Okay, so this has a negative from the right-hand rule component. Now my other pair here is going to be Ry crossed into Fx. My distance Ry is a value of 6 inches. My Fx value was 160. Again, I don't add any signs to this yet. And I take a look and I say, well, if I cross Ry into Fx, sliding my fingers along Ry, right? So your fingers should be pointed up and away from you looking at the back of your hand. You have to curl your hand till your thumb is coming up in order to bend your fingers over to the left. Thumb should come out of the screen, and so this is positive from the right-hand rule. So essentially 4 times 120 is a negative 480. 6 times 160 is a positive 960. So we end up with a positive 480. And this also is in inch pounds. We need those units, and the value is in the k-hat. The reason the value is in the k-hat here, and I could even write it at this point, this entire thing times k-hat, because we basically assigned these signs, this positive, and this negative, according to that right-hand rule, which everything is in the k-hat. And so this would be my moment at A as a vector using that principle of moments, or Varignon's theorem. Okay, so 4 different ways to compute, so this is number 4, to compute the moment around point A. I think that the easiest one for this 2-dimensional problem is this one here. But If you love spatial computations, you may think that number 3 was easiest. If you like working through a lot of angles, maybe number 2 is easiest. If you're afraid of doing any kind of manual cross products, you may think that 1 is the only way to go. They all give you the same answer. We're quite flexible in statics in allowing you to solve things however it works, okay? And so you're welcome to solve this any way that you'd like. But hopefully that gives you an overview of the different ways we can solve for moments. It'd be good of you to practice multiple of these so that you can then pick your favorite. Don't just settle upon the first one that you learned as being the only one you'll learn, because there may be some situations where one may be more efficient than others. Hope you're having an awesome day.